Welcome back. So, as we were discussing the azadirachtin case study, where the authors have selected the high yielding cell line for azadirachtin production, followed by optimization of the culture conditions for maximum productivity of azadirachtin, and then they also implemented yield enhancement strategies like precursor addition and elicitor addition to improve the yield of azadirachtin in the cell line. Then they went on to do establish batch kinetics in different types of reactors, where it was stirred tank reactor, then bubble column reactor, and even in stirred tank reactor they tried different impellers, thereby changing the mass transfer characteristics and the mixing time, and they saw the effect on the batch kinetics. So, after a suitable reactor configuration was chosen for maximum productivity of azadirachtin in batch, they also then wanted to develop nutrient feeding strategies in the reactor to further enhance the yield and productivity of azadirachtin in the reactors. Now, for doing this, one way is to do hit and trial with respect to time of addition of the feed, the concentration of the feed in the reactor, and the manner in which the feed is done. So, either one can do a hit and trial, or there can be a more rational way of simulating and coming and selecting nutrient feeding strategy based on kinetic model. They developed a mathematical model that gives an adequate description of growth and production kinetics of A indica cells in the suspension culture. Now, when they formulated the mathematical model, following points were kept in mind. One is that they did a separate inhibition, substrate inhibition study with respect to the critical substrates in the medium, to see if beyond a certain concentration the substrates were inhibiting the growth rate of the culture. Then they incorporated this inhibition effect into their batch growth kinetics, and then with the model, which was a description of substrate utilization kinetics, product formation kinetics, and biomass or growth kinetics, they simulated these equations, optimized, evaluated the parameters of the model equation. Then and they did parameter sensitivity analysis in the model to drop out the insignificant parameters, to reduce the number of parameters in the model, thereby making the model more simple for simulation. So, this was model redefining, and then finally this redefined model was used to simulate nutrient feeding strategies under fed batch or continuous cultivations. Now, before we see the case study, let us understand what is mathematical model. So, because it is a quite complex system and plant cells, they take longer cultivation times, the general experimentation is more of a hit and trial approach. Hence, mathematical model approach can give you a better understanding of the system. Now, it is based on the earlier knowledge of the system behavior, it is more therefore logical. Easy offline simulation can be done instead of doing hit and trial experiments, and thereby the number of experiments which one would take to reach to the optimum or enhanced productivities would be less. So, what they did while developing the model, they began with certain assumptions. They had the batch kinetic data and the inhibition data in batch. Now, they formulated the model equations to describe the system behavior. Then they determined the model parameters based on initial guesses. Then further these model parameters were evaluated using an iterative process, and parameter sensitivity analysis was done to select the significant parameter, thereby redefining the model. And finally, the redefined model was simulated to predict the nutrient concentrations or the feeding strategies in a fed batch cultivation and also in a continuous cultivation. So, before beginning to develop the mathematical model, they did inhibition studies in which different concentrations of the limiting nutrients were tested for possible inhibition in growth of the culture. So, this was done to account for inhibition of growth at higher concentrations of substrate which will be fed during the fed batch cultivation. So, the different model equations which were incorporated to account for growth and for inhibition were as follows. If you can see on the slide, for growth they picked up Monod's model, and for defining inhibition they picked up Luong's model and also the asymptotic inhibition kinetics. They tried to fit the data for substrate inhibition for different rate limiting substrates. So, the substrate inhibition studies were carried out with respect to glucose, nitrate and phosphate. So, the model assumptions were that the major nutrients were carbon, nitrate, ammonium and phosphate. Rest of the nutrients were available in excess in the culture broth, and the culture environment like the parameters like temperature and pH remained constant throughout the cultivation. This was the model equation used, which had the limiting terms with respect to all the limiting nutrients taken up in the model, the glucose, nitrate and phosphate concentration, and then they also incorporated the inhibition terms with respect to the same three substrate to account for substrate inhibition during fed batch cultivation. Then Ludeking Pirate model was used to define product formation kinetics. The last three equations, they demonstrate the specific substrate utilization rates, where MS, MS1, MS2 and MS3 stand for the maintenance coefficients with respect to each of the three critical nutrients, and YX by S stands for the yield coefficients with respect to substrates, and mu is the specific growth rate of the culture. A non-linear regression technique was then applied, which was assisted by a computer program to minimize the deviation between the model and the experimental values for all the data points and process variables. So, an objective function which was called as sum of squares of weighed residues was used to simulate the model. So, this was based on original method of Rosenbrock to find the minimum value of the objective function. These were the optimized parameter values of the model. Now, this picture shows that how the fitting was done using the batch kinetic data with the model. Now, the batch model was extrapolated for fed batch cultivation and continuous cultivation to develop offline feeding strategies, and then finally the selected feeding strategy which was giving maximum productivity was experimentally verified. In order to extrapolate the batch model for fed batch or continuous cultivation, this is what they used. They did the feeding of all the three critical nutrients, and this was a constant feed rate strategy, and then they defined, as done in the batch model, the substrate utilization rates for all the three critical substrates and the product formation rates. Now, being a fed batch cultivation, the dilution terms were added to the model, and then the parameters, this model was then simulated for developing nutrient feeding strategies offline, where parameters including initial working volume, start of feeding, feed rate, concentration of substrate in the feed were varied. The strategy which resulted in maximum overall volumetric productivity with minimum residual substrate concentration in the medium after a given time was chosen for experimental validation. So, the feeding strategy which was selected for fed batch cultivation was as follows. Batch cultivation was carried out in the reactor till 8th day. Then from 8th till 12th day, glucose feeding of 500 grams per liter and phosphate of 1 gram per liter was done at a rate of 0.05 liters per day in the reactor. Then from 13th to 14th day, the glucose feeding was stopped and nitrate additional feed started at 35 grams per liter, and the phosphate feed was continued but at a reduced concentration of 0.5 grams per liter with a flow rate of all the feeds at 0.05 liters per day. So, if you notice, the glucose feeding was stopped, the phosphate feeding was reduced, the feed concentration, and the nitrate feeding was started. This strategy, as predicted by the model, gave a total of nearly 22 grams per liter of biomass and 90 milligrams per liter of azadirachtin in 14 days. So, these were the conditions which were used for the fed batch cultivation, and then the fed batch cultivation was experimentally validated. So, if you see the kinetics here, the plot shows that as the feeding has started from 8th day, you can see the residual nitrate, the residual phosphate and glucose concentrations getting high, and then gradually the biomass increasing and the azadirachtin feed also increasing. Now, continuously the dry cell weight is increasing up till 14 days and the azadirachtin is also increasing continuously till 14th day, while residual nitrate was becoming limiting around 12th day. So, possibly that is the reason where the feeding was again started for the nitrate on day 12. Then the batch model was further used to develop strategies, nutrient feeding strategies in continuous cultivation, where again the same model parameters were used to design equations for the continuous cultivation, and then the model was simulated and experimentally validated. One of the strategies which could give high azadirachtin productivities than in fed batch or in batch was chosen for experimental validation in continuous cultivation. The MS medium salts with glucose of 75 grams per liter, the nitrate feed of 10 grams per liter and phosphate of 0.5 grams per liter at a flow rate of 0.5 liters per day was chosen for the experimental study. This continuous reactor which was run was a cell retention reactor setup, in which the feed was sent in the annular space of the reactor outside the filter till the 26th day, and the medium was withdrawn at the same rate from inside the spin filter. The model in this case predicted nearly 140 grams per liter of biomass and 130 milligrams per liter of azadirachtin in 26 days. So, if you see the plots, you can clearly see that as the feeding was done in the continuous reactor with cell retention, it led to continuous increase in the biomass and also in the azadirachtin productivity. So, experimentally the biomass which could be achieved was around 88 grams per liter, and the azadirachtin concentration or titers which could be achieved now were at a level of 280 milligrams per liter in 26 days. After achieving and designing nutrient feeding strategies for continuous enhancement in the productivity of azadirachtin, then the authors went on to do process integration, in which they added the elicitor and precursor selected from the shake flask studies to further enhance the yield of azadirachtin and thereby the productivity. So, the cells in bioreactors during the batch mode were treated with optimum concentration of elicitors after 8 days of cultivation. So, these elicitors were chosen from the previous study of optimization with elicitors. So, salicylic acid, jasmonic acid and chitosan were selected at their optimum concentrations based on the design of experiments. Statistical optimization was done, and then these elicitors were added on 8th day, and growth and azadirachtin production in the reactor was studied. And after addition, the biomass was nearly the same, which was 14 grams per liter, while the azadirachtin content increased to 11.5 milligrams per gram in 10 days, which was much higher than that obtained in the batch reactor in the absence of elicitor. Then continuous cultivation with nutrient addition, elicitor addition, precursor addition and permeabilization was all done together to see an integrated effect, where the cells were grown in bioreactor in batch mode, then the cultivation was converted to continuous mode with cell retention with nutrient addition of carbon, nitrogen and phosphate source with elicitor feeding from 8th till 40 days, and the cultivation was continued thereafter in batch mode till 44 days, and before the harvest of the biomass was done for azadirachtin analysis. So, if you see on the right hand side, sodium acetate was used as a precursor which was added on 2nd day, then feeding of the MS salts with glucose, nitrate and phosphate in the feed, which was optimized offline, was done from 8th day till 40th day, along with the addition of salicylic acid, jasmonic acid and chitosan, which was optimized previously using central composite design at a feed rate of 500 ml per day. Then permeability enhancers were added on 41st day when the reactor was continued in batch mode till 44th day to enable the release of the product from the cells, where 5% N-hexadecane was added in the reactor. So, what did they achieve? The maximum dry weight which could be achieved was now 62 grams per liter, and the maximum azadirachtin concentration or titers achieved were more than 730 milligrams per liter. Now, after addition of hexadecane, 751 milligrams per liter of azadirachtin was obtained in the cells from the final harvest, while 14% release in the culture medium was observed. So, this is what was done, a summary of what the authors did in this case study. They began with a high azadirachtin containing tree base cell line. They developed callus culture and then suspension culture. Among 5 different media tested, Murashig and Skoog medium demonstrated highest growth and azadirachtin production. Then optimum concentration of the medium nutrients culture conditions was obtained using statistical design of experiments, which will minimize the number of hit and trial. And then after this they were able to achieve 15 grams per liter of biomass and nearly 50 mg per liter of azadirachtin under optimum conditions in shake flask. The cells were found to be sensitive to shear, to increase in the rotational speed, where the viability were found to drop more than 85% above 150 rpm in shake flask. So, addition of sodium acetate was done as a precursor, where azadirachtin productivity was improved to 162 mg per liter in 12 days. Then further permeability enhancers were optimized and hexadecane 5% was chosen which could result in 13% release of azadirachtin in the medium while maintaining the viability up as 100%. Then elicitors were chosen and their concentrations were optimized using statistical design of experiments, where salicylic acid, jasmonic acid and chitosan were chosen. Then cumulative addition of these elicitors on 8th day for 48 hours before harvest led to the yield increase up to nearly 16 milligrams per gram. So, if you see a snapshot of how the productivity improved from in different modes of cultivations, when they did batch with cetric impeller, the productivity was 5. When they did batch with a centrifugal impeller which had improved mass transfer characteristics and mixing time characteristics, the productivity improved to 7.2. Then they did continuous cultivation with cell retention device, where the productivity was found to further improve, and then batch cultivation with elicitor addition was seen to increase the productivity to very high levels, almost doubling or 3-folds rather. Then continuous cultivation with an integrated study which included addition of elicitor, precursor, permeability enhancers and nutrient feeds led to the maximum enhancement in productivity up to 17 milligrams per liter per day. So, if you compare literature, what they found was that they could achieve maximum yields of azadirachtin in the biomass by using this rational and a more systematic manner of optimization. So, I hope this gives you an overall picture of how plant cell bioprocessing, different strategies can be implemented to achieve maximum enhancements in productivities of plant secondary metabolites.